Hello everyone, I am Mahmudul Faisal Ameen from the University of Tokyo. I'll present our work Asynchronous Unfolded Transformation for Fixpoint Logic. It is a joint work with Naoki Kobayashi and Ryusuke Sato. First, I'll discuss the background and motivation of our work very briefly. Fixed point logics are extensions of first order logic with least and greatest fixed point operators. They are interesting since program problems verification can be reduced to the satisfiability in a fixed point logic. Among the notable work on it, I'd like to mention Bjornar Atelia's work on reduction to CHC and Kobayashi Atelia's work on its reduction to mu-arith. Here is an example of fixed point logic formula. First, even and odd are defined to be the least predicates that satisfy their corresponding equation. On the other hand, dual of diff 6 is defined to be the greatest predicate that satisfies its own equation. Here, even x means x is an even number. Similarly, odd y means y is an odd number. Diff 6 is the negation of z is a non-negative number divisible by 6. Now we can have a fixed point logic formula, dual of diff 6 n or odd n. The overline diff 6 is intended to mean the dual or negation of diff 6 and not diff 6 n or even n means diff 6 n implies even n, which we would like to prove valid automatically. In the rest of the talk, we'll discuss how we aid in verification of such formulas. Sometimes, verification of fixed point logic formula becomes quite challenging. It is one such example. We'd like to check if n is non-negative, then either even n or odd n holds. It cannot be checked automatically as it is. However, if we transform it by unfolding and then folding, then this transformed formula can be easily checked. By unfolding, we mean expanding a predicate variable by the definition, and by folding, we mean the opposite, substitution of a formula by a predicate variable. Now the question is, how can we effectively find an appropriate unfolding sequence? This is the center of attention of this talk. Sometimes the transformation is not trivial. Different predicates needed to be unfolded arbitrary number of times. Consider this example. If we want to transform it, we need to unfold dual of diff 6 once and the predicate even or odd 6 times. Because we need to match the argument of even with that of dual of diff 6, that is n minus 6. Then we can be able to fold it to a simpler form that is easy to check. Now still the question remains, how can we effectively find an appropriate unfolding sequence? We call this arbitrary number of unfolding of different predicates the asynchronous unfolding. In this work, we formalized asynchronous unfolding for the first order fixed point logic mu arith. For that, we first abstracted the predicate definitions. Then we construct finite representation of unfolding sequences. We also implemented a tool, and after experiments, we found that it is indeed effective. Now I'll show how we find appropriate asynchronous unfolding sequences. First, we take the predicate definitions, and then we construct an abstraction of these definitions to a size change graph. By size change, we mean that changes of the parameters in the predicate calls are captured. In these graphs, the nodes represent the predicate variables, and the edges represent the predicate calls. The label shows the flow of data between the parameters to the arguments when the predicate is called. And the amount of change is captured here. In the next step, we construct summary information on the all possible unfolding sequences. In this example, it shows that n times unfolding of dual of diff 6 gives parameter size change of minus 6n. In another summary information, even is unfolded once, and then odd and even sequence is repeated n times for unfolding, and so the size changes minus twice n minus 1. In the third step, we take the formula to be transformed. Based on the structure of the formula, we choose appropriate summary information and discover possible concrete unfolding sequence. Here, unfolding of diff 6 once and even or together 3 times is selected as a candidate for the actual unfolding. We may have one or more such candidates. In the last step, we unfold it according to the candidate unfolding sequences and try to fold it one by one until we succeeded. It is possible to fail if no candidate works out. Now, I'll discuss a bit more in depth of some of the steps. In construction of size change graph, we capture only the constant changes. Here, in the predicate mult, x flows to the second parameter, that is y, with reducing by 1. It is captured here. Similarly, y to x with no change is captured here. Flow from z to z is not taken because the change is not constant. That's why we call it an abstraction. Notice that x is not flowing to x, but y, and y is also flowing to x, not y. So we may get these kinds of cross flow, but we need to find a parallel flow for folding, since the unfolded formula and the original formula should have similar pattern, and so the order of the parameters should be matched. In the next slides, I will show how we find appropriate composition of this transition so that finally it becomes parallel flow. For this example, 2 times, or more exactly multiple of 2 times transitions gives x to x and y to y flow. Now I will show how we summarize the unfolding sequences. Let X be a predicate, and this is its infinite unfolding sequence. X may be unfolded to another predicate Y or into itself, and it can go on. We found two interesting properties of such sequences. Suppose E is an edge of a size change graph that represents a transition. E0 is the starting point. Ek is the sequence after k times transition. Ek plus L is similar after k plus L times. We found that there always exists some k greater than or equal to 0 and L greater than 0 such that the formula after k times unfolding and after k plus L times unfolding have a pattern matching. This is the first property. Now suppose E k plus m multiply L is from m times of L unfolding after Ek. Then the particular parameter changes for these segments are the same. So that means the particular parameter changes from here to here and from here to here are same. This is the second property. And this guarantees that we can always represent all the unfolding sequences in a finite way. So for all unfolding path pi, the pi can be divided by two parts. One is the initial path, another is the repetitive path. So this path will be repeated a number of times. And in this way, we can represent any path in a finite manner. For this example of mult, we have k equals 0 and L equal 2. It gives the reflection of my comment in the previous slide that multiple of 2 times unfold of mult is necessary for folding. Here, I will show step by step how we discover the exact unfolding sequences as the candidates. I'll show by the example of diff 6. We have these two summary information. One for dual of diff 6 and the other one for even and odd. The target formula is this one. We first assume that dual of diff 6 is unfolded m number of times and even and odd combinedly unfolded n times. From the summary information, we get an unfolded formula that contains dual of diff 6 x minus 6m or even x minus twice n. Now at this point, we expect this to be pattern matched with this one. So we have x minus 6m equal x minus twice n. Now we have the constraint. There exists mn such that 6m equal twice n and m plus n greater than 0. So this part guarantees that there must be at least one unfolding of one predicate. Now by SMT, we get m equal 1 and n equal 3. Finally, we have this candidate unfolding sequence by substituting m and n. Now we unfold the formula accordingly and then fold it by substituting this part by q x minus 6. That means we get the transformed predicate q, which is defined to be the greatest predicate that satisfies this equation. This fixed point is chosen to be greatest fixed point if at least one predicate is defined with the greatest fixed point. Otherwise, if all the predicates are defined with the least fixed point operator, then we also choose least fixed point operator here. Now I'll present our experimental results. We implemented a tool based on our proposed theory. We tested it with two benchmark sets. One is our own in-house built benchmark to ensure the capabilities of the tool, and the other one is the benchmark taken from the work of Kurita and Auto. Here is the excerpt of the evaluation result of our tool for the benchmark of Kurita and Auto. Out of 31 problems of this benchmark, 28 are in our scope, and our tool can transform 26 formulas. We then checked both original formulas and transformed formulas for validity by mu-HFL. Out of these 26, 6 formulas can be checked by mu-HFL only after the transformation, not in its original form. For another 8 formulas, validity checking time is shortened after transformation. This result gives us the effectiveness of our theory. Now, I'll discuss some related work very briefly. Unfold for transformation has been studied before. For example, by Seki, D. Angelia Italia, Kobayashi Italia, and others. But our work is unique in that it addresses how to find appropriate unfolding sequences in a systematic manner. Our size change graph is inspired by the work of Lee Italia on size change termination analysis. However, our formulation is somewhat different since we capture both negative and positive size changes, and infinitely many edges are allowed since our application is quite different. Now I would like to conclude this talk by stating the main contributions of our work. We developed an algorithm for asynchronous unfold for transformation in a systematic manner. For that, we showed how we can abstract the predicate definitions to capture essential information. Then we explained how we finitely represent all unfolding sequences and then how we construct constraints from it to find candidate unfolding sequences. Finally, we presented our experimental results that gives the evidence of its usefulness. Here I finish this talk. Thank you very much.